Section 2.7, page 3. Example 4. Car A is traveling west at 50 miles per hour and car B is traveling north at 60 miles per hour. Both cars are headed for intersection C. So I've got intersection C over here. A is headed in that direction and it's headed west, which is to the left. B is headed north, which is up towards that intersection. When car A is 0.3 miles from point C and car B is 0.4 miles from point C, so they're not the same distance, how fast are the cars approaching each other? Now that might seem deceiving because they're not actually approaching each other, but they have this distance from each other. And as you'll notice, as they keep getting closer to each other, their distance keeps changing. So instead of using the phrase approaching each other, maybe we should say, how fast is the distance between the cars changing? And since that distance is getting smaller, you'll notice down below that we will get a negative answer. So we've got our picture to help get us started. And now we're going to look at all of the given information. Car A is traveling at 50 miles per hour. Now we know that car A is represented by the distance x, but because it's traveling, and we see that it's miles per hour, which is rate notation, that 50 is not x, it is the derivative of x, and it needs to be negative because that distance is shrinking. Same thing as we continue, car B is headed north at 60 miles per hour. Car B, 60 miles per hour. So although car B is represented by distance y, it's traveling, which is a rate problem, and our units are in rates. So it's not y that's 60, but it's dy dt, and it's a negative 60, again, because the distance is decreasing. The problem then goes on to tell us that car A is 0.3 miles from C, so we can go ahead and now state that x is 0.3. Car B is 0.4 miles from C, so we can now state y is 0.4. I have no other information from the problem, so I'm ready to solve an equation. With a right triangle, the only equation I have is the Pythagorean theorem, where this time I don't have a value for the hypotenuse, I still have a variable. So I'm ready to go ahead and take derivatives. I take the derivative of 2x, but need to multiply it with dx dt because I'm taking the derivative as the cars are traveling based on time. The derivative of y, multiplying with dy dt, and this time the derivative of z, multiplying with dz dt. As always, I'm going to go ahead and plug in values next, even though I'm looking for z, but not just z, the derivative of z, dz dt, but I'll go ahead and plug in values now that we've already determined that x is 0.3, dx dt is negative 50, y is 0.4, and dy dt is negative 60. We have not figured out z, and we definitely haven't figured out dz dt because that's the thing we're looking for. So just like in the past, I need to figure out what z is, but I can solve for it using the Pythagorean theorem. We already stated that x was 0.3. We already stated that y is 0.4. And I suggest watching out because a common mistake I've seen is that when people go to square 0.3, they know they get 9, but you got to remember there needs to be 2 digits past the decimal. So that's why it's 0.09. So as we do the math and take the square root of both sides, although z could be plus or minus 0.5, we're talking distance of cars, so it will not be negative. So now I can plug that 0.5 in for z, which is really just a half. So half of 2 is just 1. Doing all the math on the left side gets me down to negative 78. And since I just have 1 times dz dt, I've got my answer. And don't forget, for the units, I'm going to take the measurement of the output, which is z. Z is a distance, and all of our distances are listed in miles. and it's based on time, and the only indication of time I see in the problem is in hours, so I'm dividing by hours. Also, you'll notice that dx dt and dy dt were both miles per hour, and essentially we're just measuring a similar item, so it should also be miles per hour.